Okay, so the kind of data that we create confidence intervals for is always numerical continuous data. Things like number of years of education, age, blood pressure, and so on and something, so forth. Something that we can find a mean for, mean, median, standard deviation, and so on and so forth. There is kind of one exception to that, and it's when we have a data that is in the form of a proportion. In other words, let's say that we're sampling a population and we want to know what percentage of that population has diabetes, what the prevalence of diabetes is in that population. Well, if we sample 1,000 people in that population and 100 out of the 1,000 have diabetes, well, that proportion in our sample is 100. That doesn't mean that the proportion in the population is 100, but when you randomly sample that many people, you're going to think that you have a pretty good estimate of what the population proportion is. But in both cases, when we calculate a mean for numerical data, when we calculate a proportion for binomial data, yes or no, you have diabetes, right? Whenever we calculate those two numbers using a sample, the idea is the reason why we're sampling the population, the reason why we're so careful to take a unbiased sample, a random independent sample, is that we want to have increase our chances of getting a good measure of what the actual mean is in the population, or what the proportion of people with diabetes is in the population. So it's important to us that we manage to get as good an estimate of it as possible. In most cases, we'll never know what the true mean is. We'll never know what the true proportion of diabetes is, unless we had sampled every person in the population. And for even just calculating how many people, what percentage of Americans have diabetes, we'd have to test 350 million people to determine what percentage of Americans have diabetes. So it's not practical to do that in general. So we're always dealing with samples. Now, the problem with that is that as biostatisticians, as public health workers, we can't just rely on, I think that this proportion or this mean is close to the true population mean or the true population proportion. I think it's close. We want to quantify how close it's likely to be. That's really difficult to do. What we can do instead, because we understand how variability in a sample relates to variability in the population, and how taking a larger sample reduces that variability. We understand the idea of how samples perform. If we take repeated samples from the same population over and over and over again, we understand that those repeated samples are the means or the proportions from those repeated samples. When we put them in a new distribution, they themselves are very reliably normally distributed. So we can make a lot of predictions based on that. And one of the predictions that we can make based on that is when we find our sample mean or a sample proportion, we can calculate a range based on the way that we know samples work. We can calculate a range within which we can say with 95% certainty the true population proportion exists. Okay. Now, sometimes we want to be more. We want to be more conservative. Maybe we want to know with 99% certainty whether or not where the true population within this range that the true population mean exists. Now, let me ask you something. You guys in here, if I were to look at if this is the 95% confidence interval, so let's say that we found the average was 100 and the 95% confidence interval, sampled average was 100. 95% confidence tells us between 90 and 110, we're 95% certain that the true mean of that population lies. If I said to you, I want to be 99% confidence, I want a 99% confidence interval, is that range going to be narrower than the 95 or wider than the 95? What do you think? It's going to be wider. Why is it going to be wider? Because if we want to be more confident that we actually captured it, we need a wider range. In other words, I'm more certain if I say 80 to 120, I'm more certain than if I said 90 to 110 that I got that the mean is in that range. So the 99% confidence interval is wider than the 95% confidence interval. A lot of times we're not, we don't have to be that accurate. We might say we're satisfied with a 90% confidence interval, which would be even narrower yet. We can afford to be narrower if we're willing to give up, if we're willing to give up some of the confidence that we really capture the mean within that range, right? Remember, the mean that we know is the sample mean. It's not the population mean. We'll never know this population mean, but we can know that if we have a range within either side of that sample mean, what level of confidence that we can have that the true mean is between those two values. Okay, we're going to figure out how to calculate that. There's going to be a number of different situations that we're going to run into. I'm going to open up a little piece of paper to write on here, and I'm going to take a second to connect my tablet here. Okay, the one or two of you that are online right now, do you guys have a question about that? Do you have a comment or a question about that while I'm setting this up? Oops. One thing about USB things, it's like 99% of the time you're trying to plug them in the wrong direction. It's amazing when you consider there's only two directions. How can you be wrong, so wrong? Yeah, instead, here I am, a statistician. You're supposed to happen 50% of the time. It should be right. Seems like I'm always plugging it in the wrong way. Okay. This one, I should be able to tell. Right, there we go. Yeah, that one, this one's upside down too. I'm 2 for 2 on plugging these things in the wrong direction. Here we go. Okay. Okay, so let's think about this. There's a couple of situations that I can have. Let's say that I know that I take a sample. I'm going to say that sample size is 100 people. And I know, and that sample tells me that the mean age in that population is 40 years old. Right? Now, that's the mean of, let's say the 100 people, let's say that is the population of Brooklyn. Average age of everybody in Brooklyn is 40 years old, let's say. Okay, I want to know if on average people in Brooklyn are older than people in Manhattan and Staten Island and so on and so forth. So let's say I take 100 people randomly selected from throughout Brooklyn, and I determine that the average age is 40 years old. Okay, now there's going to be a couple of circumstances here. I understand that average, because I took a sample of 100 people, decent sized sample, that average is likely to be pretty close to what the real mean, the mean age is. It's going to be, X bar is going to approximate the mean age, right? So it's unlikely that the mean age is going to be 20 or 60. It might be 39, it might be 41, but with a big sample, I'm pretty confident I'm pretty close. But I want to be able to define where that mean is in relationship to what our sample says it is. I can't really easily say whether it's more or less, unless I take more samples, whether it's likely to be more or less unless they take more samples. But what I can do is I can construct a range from one number to another number where I can say that the true population mean, mu, is going to be between this number and this number. If I want to be 100% certain, what are those numbers going to have to be? Going to have to be 0 and 100. Well, it doesn't help me to have a range of 0 to 100, right? I mean, what does the good does that do me, right? So we're not going to say 0 to 100, but we want to know what range I can reliably say that with 95% certainty that the true population mean lies between these two values. Okay, so I'm going to start off with thinking to myself, well, gee, I need to know, since I want to know how likely it is that the true population mean is really close to 40, I need to know how variable the ages are. In other words, if the ages in Brooklyn are 0 to 150, it's going to be a lot more variability, a lot less certain that that 40 is close to the right answer than if the ages were all between 30 and 60, right? Because there's less variability in the population. There's less likelihood my sample's not going to be representative of the true population mean, right? So the measure that we use for variability in a normal distribution is we use standard deviation. When we're talking about standard deviation in the population, we call that sigma for the age in the population. That's the standard deviation of variability. When we're talking about standard deviation in the sample, we call that S. Sometimes we use SD, sometimes S, right? And again, the standard deviation, the variability in the sample approximates the variability in the population, right? So a lot of people are, if it's a wide variability, when I take a sample, there's going to be a lot of variability in the sample too, right? So that approximates the population of that approximates these standard deviation of the population. Okay, well, that's pretty interesting. But now, if I knew exactly what sigma was for the population, things would be much simpler because I know that exactly how, if I knew what sigma was, I know that whatever the mean is, I know how variable, where 95% of the samples in that population, if I took them repeated samples of size 100, how far apart those repeated samples would likely be, right? So it really helps if I know sigma. Well, in fact, we can take advantage of that if we know sigma. I am going to make believe for right now that we know that sigma is equal to 5 years. Okay, standard deviation is equal to 5 years. So now, if I know what that is, I can say to myself, I'm going to start with X bar, which is my population standard mean, which is 40 years. And I'm going to say to myself, well, I'm going to assume that the true population mean then is going to be within 2 standard deviations to the right and 2 standard deviations to the left of that, right? Just like we did with the empirical formula, except that we're not talking about standard deviations for the population. We're talking about standard deviations that we would expect to get when we repeatedly take samples of size 100. Okay, the size means everything in statistics. Sample size means everything in statistics, except that you guys probably remember that the empirical rule says 95% of the results are going to be between minus 2 standard deviations and plus 2 standard deviations, but that's an approximation. Do you remember what the number actually was instead of 2? You recall? It was close, right? What was it? It was negative 1.96 and positive 1. Ring a bell? Okay, positive 1.96. Standard deviation, not really 2. But now since we're going to want to be more accurate, we're going to go ahead and use 1.96. And where did that come from? That came from the normal distribution table. And I'm going to pull that up now just to make sure that we're all on the same page with that. Let's put this up here. And I think I have it in here. It's on Blackboard in this session also, if you want to go to it yourselves. Come on. Oh, there it is. I didn't see it. Okay, Z table. Okay, and here's the Z table for standard normal distributions, and it represents a standard normal curve, standard normal distribution, bell curve, and I can see that if I'm looking for 95% of the population being between 2 points, well, my z-score on the low end is going to be down here. My z-score on the high end is going to be up here. In either case, I leave a tail outside of that 95% on the lower end and on the upper end. And since this distribution is symmetrical, the tail on the bottom represents 2.5% of the population. The tail on the top represents 2.5% of the population. So I want to know what z-score represents the point at which we have 2.5% of the population to the left of this. Okay, well, that's what this first table is telling us is that if you have a z-score, here's a z-score. If you know the z-score, this table in here tells you the area of the curve that's to the left of that. So we want to know, we're going to do the opposite of looking up the area from the z-score, we're going to look up the area and find out what z-score it is. So we want to know what z-score represents 2.5%, 0.025. So 0.025, 0.02, here it is right here, 2.5%, 0.025. What z-score represents that? Negative 1.96, exactly what we're using. That's why we use the negative 1.96. How about on the other end? On the other end, right, we're going to want 2.5% left on the upper tail, which means, remember that this table always reads the area to the left. So that means we want to know what z-score is represented by 97.5% to the left. Okay, so that would be 0.975, 0.97. There it is right there. What is that? That's a plus 1.96. That's where that comes from. How about 99%? Well, 99% is, I'm going to tell you what it is. It's 2.58. That's the number, that's the z-score we want for 99%, because we want 0.5% in the lower tail, 0.5% on the upper tail. That's the likelihood of us, the mean being outside of that area, right, when we do a confidence interval. So 0.5% on the other, let's see what that is. 0.5%. Okay, here it is over here. It's actually halfway in between these two. I'm going to take this one as the closest, 0.05, right? I'm going to take this one. It's equal to 2.58. So when I ask you for a 99% confidence interval, you use the number 2.58 instead of 1.96. And the 90% confidence interval represents 5% in each tail, right? 10% left, 5% in each tail. And that's going to be 5% is going to be right over here. It's going to be 1.64. Right, so we got 1.96, 2.58, and 1.64. Right, those are the three numbers we're likely to run across. You know, nobody's going to ask you for a 92% confidence interval. It's almost always going to be 95%. Sometimes going to be 99%, and very super rarely somebody might ask you for a 90% confidence interval. But really not many people would use that. Okay, so let's go back here and take a look at what we were doing with our table. Okay, what did I do with that now? Is it still there? Did I lose? There it is. Okay. Snuck it behind something there. Okay, so we're going to be 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. But when I say standard deviations, I don't mean standard deviation of the population or the sample. I mean the standard deviation for repeated samples of sample size 12. And we don't call that the standard deviation anymore, even though it is the standard deviation of many samples repeated in the means that put into a new distribution. We instead call that the standard error, so we don't mix it up with the standard deviation. So the standard error is equal to the standard deviation of the population, sigma, divided by the square root of the sample size, right? So in our case here, what is that going to be? It's going to be the standard deviation of the population is 5, divided by the square root of 100, which is 10, is going to be equal to 0.5, right? So what is our 95% confidence interval in this case? Our 95% confidence interval is going to be 40 minus 1.96 standard deviations, which are 0.5, or in other words, 1.96 times 0.5. So I'll write that out. X bar plus or minus 1.96. On the other end, we're going to be adding 1.96 times standard deviation, standard error, times the standard error, right? Times the standard error. Okay, so in our case, what's that going to be? It's going to be 40 plus or minus 1.96 times standard error is 0.5. Okay, now I'm going to round this. So you would actually normally just multiply that out and subtract it. I'm just going to make believe this is 2 and say that 2 times 1/2 is 1. So our confidence interval is 39 to 41. So our sample told us the mean was 40, right? But we don't know how accurate that is. But we do know, based on the fact that we know the population standard deviation, sigma, and our understanding of repeated samples from the same population, we do know that we can predict with 95% certainty that the true population mean mu is between 39 and 40. Well, really, it's going to be 39 point, let's see, 0.4, 39.8 to 40 point, to 40 point, I'm not get this wrong, 39.08 to 40.92, something like that. It's going to be a little less, a little bit narrower, because it's really 1.96, not 2. You could actually do the calculation on your own. Okay, so that's pretty simple, right? So if I were to ask you to do that again, and I'm going to give you an example, you guys online too, give this a try. I'm going to set this up for you, and I'll try and make the numbers reasonable. Okay, let's say you take a sample, your sample size is equal to 121. Okay, and you find that X bar, let's say it's blood pressure. The blood pressure, average blood pressure for take a sample from a population, large population, the average blood pressure turns out to be, I don't know, let's see, 90. And the standard deviation for that population, maybe somebody's done a giant study from that same population, and you happen to know that the population standard deviation, again, most of the time you're not going to know this, population standard deviation is equal to, say, 22. Okay, so I'm going to ask you, what is the 95% confidence interval for the true mean for mu? Okay, you guys give that a try. Okay, I'm going to set up the formula here. X bar plus or minus the z-score for alpha equals 0.05, 95%, right? That 5% chance of being wrong, times the standard error. So the first thing you guys are going to want to do, you want to calculate the standard error. And then once you calculate the standard error, you want to put in the right value for z and the right value for the standard error. I'll give you a minute or two to do that. I'm not going to put you on the spot. I just want you to give it a try. I'll give you a minute or two, and then I'm gonna go ahead and finish it up. Okay? You don't have to get the exact answer. Okay. Okay. Should I go ahead? Okay, good. Okay, so what's the first thing we got to do? We got to calculate standard error, right? Because we knew the population standard deviation, but we need to know the standard error, the standard deviation for repeated samples of that size. That's called standard error. So the standard error is going to be equal to sigma over the square root of the sample size, right? So that's going to be equal to 22 over the square root of 121. What's the square root of 121? Yeah, exactly. The square root of 121 is 11. That's why I picked it. It's going to come out to a nice even number. So that comes out to be, the standard error comes out to be 2. So X bar, the mean is 90, plus or minus, since it's a 95% confidence interval, and we know the population standard deviation, we use 1.96 for the Z value, times the standard error, which is equal to 2. Okay? Yes, for 95% confidence. Okay? If I had said 99%, what would it be? Remember? 99 was 2.58, and 90% would have been 1.64. And notice what happens. If you make that a 2.56, right, and multiply by 2, it's going to be wider, right? So you know you go in the right direction because 99% confidence interval is going to come out wider. Okay, so what's this? This is going to come out to be 90 plus or minus 1.96 times 2 is going to be 3.92, I think, right? 2 carry to 1, 18, 9, yeah, 3.92. So what's our 95% confidence interval? It's going to be 86.08 to 93.92. Right, great, right? That's our 95% confidence interval. It's that simple. And if I had said 99%, only difference would have been 99%. The only difference would have been that the Z-score we're going to use is 2.58. 2.58. Let me rewrite that so you can read it. 2.58. And the 90%, if I asked for 90% confidence interval, the Z-score would have been 1.64. That's the only difference. Okay, pretty simple, right? No great shakes here. Easy enough. All you got to do is recognize sample size and that you know the population standard deviation and so on. Okay, so now I'm gonna throw a monkey wrench into this whole thing now. Actually, before I throw a monkey wrench into this whole thing, I'm gonna do the same thing now with proportions. Okay, now with proportions, right? With proportions, normally when you do a survey that involves a binomial value, like yes or no, are you left-handed or right-handed? Have you ever been told you have diabetes? Have you ever been in a car accident? When you do that kind of survey, usually you're dealing with very large samples. So for instance, let's say I ask you if you're going to vote in November. I want to know what's the probability that registered voters in Brooklyn are going to vote in November. I keep picking Brooklyn. I grew up in Brooklyn. I live in Queens now, but my heart is still in Brooklyn, you know? I still don't know how. I've been living in Queens for over 30 years now. I still don't know how to get around Brooklyn, Queens, with all these mixed up streets and weird intersections and stuff like that, and so many different neighborhoods. I guess Brooklyn's the same way if you grew up in Queens and went to Brooklyn. But at any rate, let's say you're interested in knowing how many people among registered voters. You're going to do a survey, registered voters. You want to know what percentage of them plan on voting. Okay, so you do a random sample, a telephone survey of 1,000 voters. Okay, so we've sampled 1,000 voters. And you find that out of those 1,000 voters, that 400 of them tell you that yes, they plan on voting. And 600 of them tell you, no, I don't plan on voting. So what's the probability that any random person that you select from this population is going to vote in the next election? What's that percentage that's going to vote? 40%, right? 400 out of 1,000 is 40%. So the probability that any random individual in this population is going to vote is 0.4 or 40%. Okay, now notice I used P. Remember before I was very careful that if I talked about the mean, population mean, I used mu. And if I talked about the sample distribution mean, this sample mean, I used X bar. I got the same problem with this. P represents the population proportion. So to distinguish, which I'll never know, P I'll never know because I'd have to sample every voter in Brooklyn to know what the real percentage of voters is going to be. And you'll know on November 2nd, they actually do that. You know, they vote, you'll know on November 3rd, you know, what that proportion was, but you won't know before that, right? That's why we're doing the survey. Okay, so I need to distinguish this. So the way we distinguish it, like with the mean, sample mean, we put a bar over the top. With the sample proportion, we put a little cap like that. That represents, P cap represents the sample proportion, and just P represents the population proportion. Okay, so now I've taken a nice big sample, 1,000 people. I know the sample proportion is 0.40. And I know enough to say that's a nice big sample. It approximates what P is, the population proportion. But I need to know more. I need to be able to quantify what my certainty is that I'm close to it, or how far am I from this? How variable could it possibly be? So I need to do the same thing with the sample proportion that I did with the mean that I did before. So what I'm going to do is I'm going to set up a similar equation. The sample proportion plus or minus, I'm going to create a confidence interval for a proportion, plus or minus 1.96 for a confidence, 95% confidence interval. I'm going to use 1.96, the z value for that, times the standard error. Okay, so let's see, let's calculate that out. My sample proportion is 0.40 plus or minus 1.96 times the standard error. Well, how am I going to calculate standard error here? No one told me what the variability was in the population. How am I going to calculate that? Well, we have a formula that we're going to give you that says the standard error for proportions is equal to the square root of P, the proportion, times 1 minus P over the sample size. Okay, now, did I put P cap or P, just P in there? I put the population proportion in there, right? P. But we don't know the population proportion. So we're forced to use P cap because that's all we have, right? So the standard error is equal to the square root of 0.4 times 0.6, 1 minus P, over 1,000. Okay, and I'm not gonna try and do that in my head, so or it's left of my head at my advanced stage. Okay, so I'm gonna do, oops, that got away from me. Try this again. Okay, good. Okay, so I'm gonna do that now. Let's see, first I'm gonna clear everything out. So I did something before. Okay, so 0.4 times 0.6 is equal to 0.024 divided by 1,000. 1,000 equals, is it going to be equal to 0.00024? Now I have to take the square root of that, right? I'm calculating everything that's inside there, and I got to take the square root of it. And my little scientific calculator let me do that. And the answer is 0.01549. 0.1549, it's halfway between, I'm going to call that 0.0155. Okay, rounded off to 3 significant digits. 0.0155. Okay, so my standard error is equal to 0.0155. Okay, so now I'm going to put that in here for my standard error, 0.0155. So I'm gonna calculate that. Okay, I should have left it there. Okay, 0.0155 times 1.96. That's equal to 0.03. I'm just going to round that up to 0.03. Okay, this whole thing here is equal to about 0.033%. So our 95% confidence interval is going to be 0.40 plus or minus 3%, which is going to be 0.37 to 0.43. So I'm 95% confident that the true proportion of people who are going to vote in Brooklyn on November 2nd is between 37% and 43%. Right? Do I know if it's 37 or 42 or 41 or 38? No, all I know it's somewhere in that. I'm 95% sure it's somewhere in that range. But that's useful to me because what I can tell you is less than half the people are going to vote. I'm 95% sure less than half the people are going to vote. Because if I'm 95% sure it's between 37 and 43, I know it's not 50%. At least 50. I'm 95, at least 95% sure it's not 50%. So you see how this can be useful, the confidence interval can be useful to us. In other words, if I were to tell you what we were interested in was whether or not more people would vote in Brooklyn, a higher percentage of people would vote in Brooklyn versus Queens, right? If I told you that, well, 50% of people in Queens are going to vote, right? What about Brooklyn? Well, Brooklyn, based on what we know, 37 to 43%, we're 95% sure that's a percentage. So we're also 95% sure that fewer people are going to vote in Brooklyn than are going to vote in Queens. So that's how we make use of this. Now, if I had told you that we know for a fact that 42% of the people in Queens are going to vote November 2nd, can you tell me that the percentage is different in Brooklyn than in Queens with 95% certainty? You can't, because our range for what the population proportion is going to be is between 37 and 43. We couldn't tell you that it's not going to be 42, right? That's inside of our confidence range. So in that case, I can't say with 95% certainty if Queens is going to have 42% of the people voting. I can't say with 95% certainty that it's going to be different in Brooklyn, right? Because it could be that 42%. That's inside the confidence. That's why it's important whether things are inside the confidence interval or outside the confidence. And that's why we do this, because we do this to be able to tell if when we take a sample from one place and a sample from another place and we want to compare them, whether we can say with certainty or with the level of certainty that will satisfy us that those two results are different, that this group scores higher on the test than this group, that this group has a higher average BMI than this group, BMI than this group, and so on and so forth. So that's why we do this. So we know what level of confidence we have that two groups are different. That, for instance, people taking this drug have more of a drop in blood pressure than people that take a placebo with a certain level of certainty, right? We always got to do it. You take a sample, two samples are always going to be different, but you need to know if they're different enough for you to be able to help. Now, we don't just use confidence intervals. We'll learn something about the t-test. Confidence interval is very useful for us to understand this. Now, I wanted to find one other thing for you. You see this number over here, 0.03, which is really 1.96.0155. That number that we add and subtract to the proportion or to the mean, we give that another name, ME. Got any idea what ME might stand for? Right. If I said to you, I think that person takes a size 8 shoe plus or minus one size, what would you call that? How about margin of error? Right. The margin of error is, right, ME stands for margin of error. So this number in here, the term we give this number in here, is the margin of error, the plus or minus, the range either way that we think it would be. Okay, so how you guys feel about this? Are you okay with this?
Yeah.
I don't hear a lot of confidence there. Okay, in that case, we're going to do one more. Okay, I'm going to give you a proportion this time and a sample size. You're going to tell me what the 99% confidence interval is, okay? Sample size is equal to, let me take a number here. Let's see. 100. Sample size is 10,000. Right? And the population sample proportion that's a really big sample, right? Then maybe that's too big. That's okay, I'll leave it that way. Population proportion is equal to, I don't want that. I'll leave sample size 1,000. I'm gonna have to use a calculator anyway. Sample size 1,000, the population proportion, let's say Let's say I'm surveying HIV status in the South Bronx, and the population proportion of people in my sample who are HIV positive is, I'm going to say that it's 8%, 0.08 is 8%. And now I want to know what's the 95% confidence interval. Nope, I say 99. 99% confidence interval for the true population proportion in the South Bronx. Okay, so I'll write the formula down. You guys take it from there. Okay, P cap plus or minus. Okay, and I'm going to put the Z in here. You tell me what Z you're going to use times the standard error. Okay, and I'm going to write here the formula for standard error again is equal to the square root of P times 1 minus P over N. How are we doing on time here? Not great. You're going to need a calculator for this one. If you don't have one, just lay it out, write it out, write the formulas out, stuff like that, just to make sure, because then you can always later on go through the operation with the calculator. Geez, this is like a private tutoring session, right? This is cool. The other 12 of you should stay home. We're having a great time in here. The air conditioning's good. It's raining out anyway. I know you're not out having a good time because it's raining. Okay. All right. I got to give this a try now. Okay. So P cap is 0.08, right? That's what the proportion of people who were HIV positive in our sample. So really what that would have meant, that would have been like as if we had out of 1,000 people, we had 80 people that are HIV positive, right? 80 out of 1,000 is 0.08. Do I have that right? Yes, that's 8%. Right? Okay, so 80 out of 1,000 people were positive. That would be P cap is 0.08. Okay, so 0.08 plus or minus. So the Z value that I'm going to use for 99% confidence interval is going to be 2.58. Had we said 95% confidence interval, we would use 1.96 plus times the standard error. So our standard error is going to be equal to the square root of 0.08 times 0.92, right, 1 minus P, over the sample size of 1,000. So I'm going to go ahead and do this. Calculator. And oh, there's my calculator. Good. Clear, clear, clear. Okay, so 0.08 times 0.92 divided by 1,000 is equal to that. Take the square root of that, and the value I'm interested in is 0.0086. I'm going to use 0.0086. Okay, so this is going to be 2.58 times 0.0086, a little less than 1%. Okay, but I'm going to multiply by 2.58. Okay, so I still have this here, so I can just go ahead and multiply this number by 2.58. In fact, it'll be a little bit more accurate if I do that because I haven't rounded. It's always good practice in statistics to not round if you can. That's why I like using it. You see me use Excel quite a bit because Excel, no matter how I format it, show me one decimal place, show me two, it always saves the whole real number right in the background. So I don't have to round. I can just do calculations, not worry about rounding. And then round, if I really want to round, just round at the very end. The reason for that is why that's important is because statistics, we're doing a lot of stuff like squaring numbers, taking square root. So if I were to tell you that something was 3.6, and then you squared that number, if I told you, let's round it to 4, and you squared that number, well, the square of 4 is a lot different than the square of 3.6. So you tend to multiply when you round things in the middle of a calculation, you risk like really multiplying the error, right? So it's always good to wait to the end, but within reason, we can round things if we need to in the middle. Okay, so that comes out to be 0.022. I'm going to round now, 0.022. So this whole thing is equal to 0.022, right? So plus or minus 0.08, plus or minus 0.022, plus or minus about 2%. What is this called over here, the 0.022? Bingo, margin of error, exactly right. That's the margin of error. Okay, and what is that going to be equal to? It's going to be equal to, let's see, 95% confidence interval is going to, 99% confidence, it's going to be 0.058, am I right? To 0.102, from about 5.8% to about 10.2%, right? So we may not know what the true P is. We'll never know what the true P is, but we're 99% sure is between 5.8% and 10.2%. That's what confidence intervals are all about. Now, if I was willing to be only 95% certain, I could have used 1.58 there. I'm sorry, 1.96 there, times 0.0086, right? And what does that come out to? What did I do my calculator? Okay. Oh, I'm going to divide that by 2.58. It should bring me back to my original number. Yep, it did. Okay, now instead, this time I'm going to multiply the original number, but the original standard error times 1.96. I'm going to multiply it by instead of 2.58. And it comes out to be 0.017. Okay, so it's going to be 1.96. I'm sorry. It's going to be 0.08 plus or minus zero point 0.1. What did I say it was? Remember? 0.17. 0.017. Okay, so what's our confidence interval there? It's going to be 1.7 under this, which is going to be 0.063 up to 0.097. Our 95%, we can be 95% certain that it's between 6.3% and 9.7%. It's a narrower range, but we're not as certain. If we want to be more certain, we have to have a wider range, right? That's why the 99% confidence interval is wider than the 95% confidence interval. And whether we use 1.96 or 2.58 is determines how much wider or how much narrower that it is. Okay, now I'm going to throw a monkey wrench into this whole thing. Okay, we're all satisfied. We finally learned how to do this. And we're all confident now and stuff like that. Now I'm about to mess this up. Okay, I'm not really going to mess it up because it's really not going to be that different. Okay, now remember I said to you, I'm going to go back. Let's say I take a sample from a population of size 100. You want to know something? I don't want to take size 100, right? I'm going to say take a sample of size 25. Remember I said size 100? Size 100 is a pretty big sample. I'm going to take a small sample. In fact, it's more common that you'll be working with small samples than really large samples very often in statistics. Okay, so our sample size is 25. And I'm going to say we're measuring the blood sugar in a population, elderly population, all the seniors in New York City between 60 and 80 years old that are residents in nursing homes. And I want to know what the average blood sugar, fasting blood sugar is for that population. Turns out that we take a sample of 25 randomly selected people in that group, and X bar, the average blood sugar level, is, I'm going to say it's a little high, is 110. Okay, so I say to myself, okay, that's great, it's 110. So now, what is mu and what is sigma? Well, remember before I told you what sigma was, right? I told you mu, we're not going to know what mu is. We're going to calculate the confidence interval, but I told you what sigma was. Well, this time we don't know what sigma is either, right? We do know that the mean is approximated by our sample mean. And we do know that the standard deviation, sigma of the population, is approximated by our standard deviation for our sample, right? But we don't, now we've taken away an element of certainty. We've added more uncertainty because we don't know what sigma is. We have to depend on our sample to estimate it. So now we have two things we don't know precisely. We don't know the true population mean precisely, and we don't know the true population standard deviation precisely. So now we got a problem. We're going to calculate our standard error based on not on sigma over the square root of n, but on the standard deviation of the population over the square root of n. Okay, so let's say I told you that standard deviation of the population was, let's see, 10. Okay, standard deviation of the population is 10. So what is our standard error going to be? Our standard error is going to be equal to 10 divided by the square root of the sample size, which is 25. That's 10 over 5 is going to be equal to 2. That's our standard error. So I'm going to set up my confidence interval. My confidence interval is going to be X bar plus or minus 1.96 times our standard error. Oh, wait a second. I got a problem here. I use 1.96 because it is the standard normal distribution, right? That's when I know what sigma is, I can use the standard normal distribution. But now the distribution I have is not so reliable because I don't know what that is. All I know is an estimate of it, S, right? So I have to adjust my 1.96 for the sample size. In other words, the bigger the sample size is, the better that I know the value I should be using here for my margin of error. Now, that means that if our sample size is small, this number is going to be bigger than 1.96. If our sample size is larger, but still not gigantic, it's going to be getting closer to 1.96, but the best it can be, if we sampled everybody in the population, we would know what sigma is, and this would be 1.96 again, if we don't know sigma, right? So we need to know what to use here, right? Standard error we calculate this way. We have no choice because we have to use standard deviation in the sample because we don't know what this is, right? So we have no choice there. That's going to be equal to 2. What number should I put in there? We call that a different kind of distribution. We call that a t distribution, okay? And it comes from this fella that did analyses with this guy Student. That's a pseudonym, by the way, Student. He actually worked for a brewery, and they breweries. You ever see that commercial that's on now where it's some German beer? The woman is explaining that now we use computers and sophisticated equipment, and we can test new brews within, for alcohol content and flavor. We can test them in days now. It used to take us a year to test a new brew because we'd have to make so many samples of it. And now they got all this, they're using statistics and they've got computers and stuff, and they can do it much quicker. Well, it's the same kind of, he worked for a brewery, and they would make small batches they would have to test them and see what the temperature, if they brewed at this temperature versus this temperature, how did it affect the alcohol content and so on and so forth. So he was frequently working with small samples, right? So he developed a method, a system of statistics, this t distribution, to help him deal with samples that were small in size, as opposed to, when you take a big survey and you have a big sample. So, and he developed something called a t-test. We're going to talk about that going forward. But right now, we're just interested in t distribution. So what does this t distribution look like? The t distribution, okay, here's the standard normal distribution, right? And the t distribution represents the standard deviation for all these different sample sizes. This is the optimal. This is the standard normal distribution. If you have a very small sample size, that distribution of sample means is going to look more like this. It's going to be much wider. And instead of using 1.96 to tell you where 95% of the samples are going to be falling, you're going to have to go out wider and use a different number for that. And the thing is there's not a single standard normal, there's not a single t distribution. There's a t distribution for every different size sample size. So here, look at all, depending if this is a sample size of 50, this might be the t distribution. For a sample size of 30, this might be. For sample size of 25, I'm sorry, it's the opposite direction. For a sample size of 25, it's very wide. For a sample size of 30, it's a little less. For sample size of 25, it's getting close. As we get, sample size of 50, it's getting closer to the standard normal distribution. When you get to a sample size of 100, it's very close to the standard normal distribution. Still a little bit different, but very close. So we need to know what number to use. Instead of x bar, we're looking at x bar plus or minus the z distribution. We're looking at x bar plus or minus the value of t for certain sample size and for 95% for 0.05 chances of being wrong, being outside of that. 95% certainty, 5% chance of being wrong. That's the t value you want to put in there times the standard error. Well, how do we figure out what that is? We have a table which summarizes the t value for all these different sample sizes. Here's our t-table. There's one in, I like to use these tables from Agresti only because this textbook called Agresti, or the author's name is Agresti. Just because I'm used to it and they're handy, and I have them scanned and as PDFs on here. There's a similar table in your textbook as well. But you can use these. These are on Blackboard. I put these on Blackboard. So what determines what that number is? Well, I'm going to, first of all, number one, we have a column here for all the common confidence levels you might want to work with. 80%, 90% confidence, 95% confidence, not surprisingly, is right in the middle. 98% confidence, it doesn't come up too much. 99% confidence, and so on and so forth. Well, what if we wanted to know what the confidence line? Here's a sample size over here. Only thing, it doesn't say sample size, does it? It says instead DF, degrees of freedom. Okay, you can think of it this way. It's a little bit of a complicated idea, but you can simplify it and think of it this way. If I gave you one candy, right, and put my hand out, you got one candy, you don't have any degrees of freedom. If you want the candy, you got to eat that candy. If I put two candies on there and tell you you can have one, now you have 1 degree of freedom. You can choose one or the other. If there were 10 on there, you could choose one. Well, now you have 9 degrees of freedom. So it's one less than the sample size. So the number of degrees of freedom for sample size of 25 is going to be 24. So we're working with 24 degrees of freedom for sample size of 25. So what is the t-value that we're going to need for 95% certainty? Okay, well, I'm going to go down here and across here, and it's going to be 2.064. Okay, that's different than 1.96. It's a bigger number, so our confidence interval is going to be a little bit wider. Why is it going to be wider? Because we have to adjust for the extra uncertainty for not knowing the population standard deviation. And when the sample size is small, that uncertainty goes up. When the sample size is larger, that uncertainty goes down. If I ask you about a sample size of 10, would that number be bigger or smaller, do you think? It's going to be, I didn't hear you. Bigger. You agree? Big. Why is it going to be bigger? Because you got to go further. It's more. You got to make it wider to make up for the larger amount of uncertainty. A confidence interval has to be wider to make up for the uncertainty that you add by having a really small sample and not knowing what sigma is. And in fact, if you look, 10 sample size 10 is 9, and the value you should be using in that case is 2.26. What about a sample size of 3? Wow, look at that. Sample size of 2, it really blows up. But sample size of 2 is ridiculous anyway. It really blows up. How about if you have a really big sample size? I'm going to go down here. How about a sample size of 100? It's 1.98. Look how it's getting closer and closer to 1.96, because the bigger the sample size is, the more certainty that you're going to be close to the population standard deviation, sigma, right? So in fact, you get to 1.96 when you have a sample size that's infinite, or the entire population. By infinite, they mean not really infinite, but if you measure the entire population, you know what sigma is, right? So you can use 1.96. But you know, when you get a sample size of 100 or bigger, a lot of people will just use 1.96 because it's so close. Especially if you're going through, you're just estimating it. You're testing your initial look at your sample or something like that. So for our example, we are going to be using the value. We're going to be using the value 2.064. Because the first two columns are for 80% confidence level, 90%, and 95%. If we were doing 99%, it would be this confidence level. So for us, 24 degrees of freedom, we're using 2.064. If we wanted to be 99% confidence interval, we would use 2.797, which is bigger than 2.58, which we would normally use if we knew what sigma was. Okay, so what did I say, 2.064? Okay, so what is our confidence interval going to be? It's going to be 110 plus or minus 2.064 times our standard error, which we calculated was equal to 2. So it's going to be 110 plus or minus 4.1. It's going to be 128, 128, I think, right? Yep. Okay, which is going to be confidence interval then is going to be 114 point, I'm going to round it off at this point, 0.1, and I'm going to subtract 4.1 from this, and it's going to be 105.9. So our 95% confidence interval is going to be 105.9 to 114.1. I think, assuming that I haven't made a math error here. I don't think I have. Okay. So that's what happens if you don't. And the thing here is your decision tree, right? Is number one, do I know what sigma is, the population standard deviation? If you do, you use the z-score, use 1.96. If you don't, you got to go to the t-table. And when you use the t-table, how do you decide what value to use? Well, you look up for the number of the sample size or degrees of freedom. You look up what the value is going to have to be for 95% confidence interval. And you use that in your calculation of your margin of error.
Every freedom has to be every degree of freedom
has a different number, yes. Every sample size has a different t-distribution, because every sample size has a different level of certainty for knowing for how well you know the population standard deviation. If you take a sample size of 100, you have a much better picture of what the population standard deviation is. You got a much better look at what that sample distribution looks like. If you have a sample of only 9, sample size only 9, you don't have a very good look. So it's going to be wider. And 8, it's going to be even wider yet. 7, 8, whatever that number is, that sample size is going to be for each sample, each number size in that sample size, there's a separate t-distribution. Now they could have given you a book which had a table just like the z-table for every sample size, right? For sample size 11, here's 2 pages. For sample size 12, here's 2 pages. But they didn't bother with that because for the most part, the only thing you're going to care about is what you need for the 95% confidence interval or the 99% confidence interval. So instead, they summarize those important values, what we usually in statistics call critical values. They summarize them in this table, so you wouldn't have to have a book full of tables because you don't care. Like, we did these examples where, oh, well, what's the area for, if it's z is equal to 2.1, what areas to the left of that and the right of that? Most of the time when you're doing confidence interval, you don't care about any of that stuff. All you care about is what is that range, that 95% confidence interval range. So all you care about is the values for your sample size. What do you have to use for in place of z, to calculate the confidence interval? So you get 1 table instead of 100 tables. Now, on the other hand, you'll notice that as you go up in sample size, they jump from 40 to 50 and 50 to 60, and so and then 60 to 80, 80 to 100, right? So you might have to use your judgment to decide which one you choose. Now, you could either just choose, like, in other words, if the sample size was 55, right? You could choose 55, you could choose 50, or you could choose 60, 2.09 or 2.000. Which of those would be the safer or more conservative choice? 60 would give you a smaller number in the narrow confidence interval. So you would go for the lower number, 50, right? Because that's the more conservative choice, because that'll give you a wider confidence interval. You'll be less likely, if you're saying 95% confident, you'd be less likely you would be lying. It'd be a small lie, but it'd still be a little tiny lie because it's not, you're really in between those 2 numbers.
The list of the sample size is 26. We don't always have to look at 26. We have to look at 25.
Right. Yeah, whatever the sample size is. If the sample size is 48, you would look for 47 degrees of freedom. If the sample size were 30, you would look for 29 degrees of freedom. Okay. So it's just the way this table is, right? They could have put just n here and said instead of 1, say 2. right? Or instead of, and 3 and 4 and 5. They could have done that, right? Put another column here with the sample size. But the understanding is degrees of freedom is represented by the sample size minus 1.
Okay, if you give us like a sample size of 50,
49.
and we don't have 49 here.
Yeah, but then you got to, then you can say to yourself, well, what am I going to do? Am I going to use 50, either 50 or 49? Well, there's two things you could do. One is you could say, I could play it safe and say 40, because that'd just make it a little one, right? Or you could say, yeah, I'm so close to 50, I'm just using this number. Or you can interpolate. That means when you say to yourself, the difference here, 40 and 50 is 10, and the difference here is 11, you could say to yourself, well, 49 is, since this is 11, this is 10. It's like 41, 42. Each step here is 1/10. Each step here is 1 out of 11. So you could just say, well, 49 would probably be about 2.08. You could kind of interpolate. There's another thing you could do, which is in Excel, you could look up the actual t-value in Excel. Oh no, I was afraid you're gonna ask me how. there's a function. I'm joking. There's a function in Excel that you can use. Okay, I'm gonna open it up. Let me increase my view here. Oops. Oh, here, it's a little bit large, I guess. Okay, equal. Let me see if I can remember it. T-dist parentheses and degrees of freedom. Okay, value x. So, here's a freedom entails. No. Okay, let's see. T-dist. Let's say, I think this is the one I need to use. Let's say 0.95, comma, degrees of freedom. I'm going to use 49, the one you just brought up, comma, tails, 2 tails. 2 tails meaning we're looking at both ends. And there's a t, no, I got that wrong. That's the equals t inverse, parentheses, probability 0.95, comma, degrees of freedom is 49. Nope, that's not it either. That's the area. Let me look it up. I don't remember. To be honest with you, you don't have to worry about using it. Somewhere in there, one of the versions of the t-dist, one of the t-dist, t-test, t-dist. I think it was t-dist. I'll have to look it up. I don't remember off the top of my head. But I'll figure it out. I'll try and remember to figure it out, and I'll post it on Blackboard. Okay, but don't worry about it for now. Well, I will be going over the Excel on how to do various functions on it, including confidence intervals and t-tests later on when we go, probably the next session, right? We'll be doing that. Now, I did want to mention that I'm going to be posting the exam on Wednesday. You'll have several days to do it, probably from Wednesday night when I post it until, since the weekend, close to the weekend, maybe I'll let you do it through Sunday. The way it's going to work is open book. You can use anything on Blackboard, a textbook, or whatever. You can't collaborate with anyone on the internet or outside or other students. You've got to do it on your own. You're going to have 2 attempts, right? After the first attempt, it'll tell you which ones you got wrong, just like the homeworks tell you which one you got wrong. And then you'll get another attempt to do it again, right? It's going to start from scratch. You got to remember to do that. It is timed. You'll have 2.5 or 3 hours, whatever I set it up for, depending on how many questions I put on it. You have 2.5, 3 hours to do the exam in one sitting. In other words, once you start, timer starts. And it's just like you would take in a real exam. Okay, you do it on Blackboard. Timer starts, and you got 2.5 or 3 hours to do the exam. I don't think it'll take anywhere that long, but you have that time if you need it. And then at the end, and when you're done, you hit submit, right? If you don't hit submit, after that requisite amount of time, it'll just self-submit, right? So it's like, Cinderella with the ball and so you'll turn into a pumpkin. Huh?
Would that include us using Excel as ESS?
You can use anything you want. Okay, you'll be on Blackboard, but you'll be able to work with any application that you want. You can use Excel, SPSS, and so on and so forth. If anything, I don't think there'll be much SPSS on this exam. You're going to have a lot more of it on the second exam. right? A lot on the second exam, right? So you can relax on that a little bit, right? I may give you a table or interpret or something like that, but we'll see. I'll give you more information about it when I post it on Wednesday. Z table, okay. I'll tell you what. I will at some point be, like probably on Friday or Saturday, something like that. I'll do a review session. If you post, remind me to say, please, do some problems using the Z table, and I'll make sure, even if you can't be there at live like you are now, right? I will review it so you can watch it. I'll post it and you can watch the video afterwards. What's that? Well, you'll have at least, in other words, you can either wait until then to take the exam, or you can do your first try, and then save your second try until after the review session. Okay? Can't wait forever. We only got 8 weeks here. Okay, so hey, listen, I got another class. They're doing it at School of Public Health, 5 weeks, right? 5 weeks is ridiculous. Yeah, exactly. Well, anyway. I didn't say it's ridiculous. So whoever's listening in from School of Public Health, I don't mean it's ridiculous, but it is ridiculous. So at any rate, it's nice for the students can get done quickly and move on, but I mean it's just brutal. Of course, you can ask me more than
one. When you were drawing, right? So there's a formula x bar plus minus t.
Yes.
And then it follows with n and then 0.05.
Yeah, you know what that stands for?
No.
In other words, the t that you're going to use is dependent on the sample size n, okay, and the confidence interval. So n is the sample size, and comma, the 0.05 is the alpha error. In other words, the probability that you'll be wrong, that the mean won't wind up within that confidence interval. So if you're 95% sure it's in that confidence interval, that means there's a 5% chance you're wrong, and it's not.
Is there a number we have to calculate there? Or
No, yeah, that's just a way for you to remember, oh, the two things I need to know for this for T is what my level of certainty has to be. I put it down as the alpha error. Instead of 95%, it's 0.05. Yeah. And the N is the sample size. Both of those you kind of convert in your head. The 0.05 you got to convert to saying, oh, that means 95% confidence. And the N, you got to convert to degrees of freedom, and n minus 1, when you actually look it up on the table. But that's kind of, I'm cheating a little bit even on that nomenclature, but that's kind of the way that the textbook will show you that I'm doing that on purpose because I want you to feel comfortable in case you see it in a similar form in the textbook or online or something like that.
As long as you don't have to multiply.
No. That just means use the t-score that's appropriate for this sample size and this level of certainty. Yeah. Okay. Now, what I would like to do now is for the guys online and for us here, I'm going to start. First of all, number one, we're going to take a 10-minute break, right? Because I think we could use a break. Okay. And then I'm going to play a video lecture that Levi gave on this material. Okay. The lecture lasts for about an hour. I may scrub through some areas of it if it gets bogged down or something, but I'm going to have the guys online. So whoever's online, if you're still online, it is now 6:57, 7 o'clock. Come back at 8 o'clock, and we will have at least kind of, watch most of that video, if not all of the video. We might scrub through some sections of it, but most of that video. I think it'll last a little bit more than an hour. Okay, so we're going to take a 10-minute break. The guys online are going to be watching it on their own computer. So I'm going to pause recording, and we'll be back at 8 o'clock.
This conference will now be recorded. This conference will now be
recorded. I'm going to take
recorded.
a look at this from the perspective of repeated samples, the sample means, right? So now this distribution represents all of the possible sample means of size, say 25, right? So let's say that we know the original population has a standard deviation that's equal to 10. Right? If we take repeated samples and mu is equal to, what did I call it before? I called it 60, right? 60. Okay, let's say mu is equal to 60, standard deviation is equal to 10. Same population as before. If I take repeated samples of size 25 from the population we spoke about before, and I made a new distribution of only the sample means, not the individual people, but only the sample means. Well, now my mean would estimate the sample mean. Sometimes I get a little less than 60, sometimes a little bit more, but on average, we would get a mean of 60 for our samples, right? So, but our standard deviation or standard error, we're going to call it now, our variability for these repeated samples of size 25, our standard error is going to be equal to the standard deviation divided by the square root of the sample size. Or in other words, 10 divided by the square root of 25, which is 5, which is going to be equal to 2. So that tells us, if I ask you now, if I took a sample from this population of size 25, what's the probability that our sample would be 59, have a mean of 59 or less, right? Well, again, I'm going to calculate a z-score. Z-score is 59 minus the mean 60 over the standard error, because the standard error is the standard deviation for this sample distribution, which is 2. So my z-score is equal to 1 over 2 or minus 1/2, right? So I go to the t-table, minus 0.5. Do I have it still open? Yeah, I think I do. Minus 0.5. Hey. Okay, so let's look up minus 0.5. Minus 0.5, 0.50 is 0.3085. So this area is going to be 0.3085, right? So in other words, the probability that I would get a sample, take a sample of size 25, and it'll have a mean that's less than 59 is going to be about 31% of the time. And 69% of the time, it's going to be more than 59. And 31, and 19% of the time, it's going to be between 60 and 59. How do I know that? Because from here down, it's 50%. If this is 31, that leaves 19 in there. Okay? That's really all you have to worry about. We're doing the same thing we did with the normal distribution for the entire population, except we're using the standard error instead of the sigma, because we're dealing with repeated samples. Not the real population, but repeated samples from that population. Okay, so guys online, guys, any guys over here and anybody else? Okay, so I will be putting up, I'll be posting the exam on Wednesday, as I said at the beginning. You'll have 2 attempts at the exam. It's open book. You can look up anything you want on Blackboard or whatever's linked from Blackboard directly. You can use a textbook. You cannot communicate with or collaborate with other students, other people, your grandfather, the dog, anybody like that. Okay, even if you have a very smart pet, they're out. You can't talk to them about this. So you'll have 2 attempts. I'll try and do a review session in the middle sometime, like maybe Friday or Saturday, something like that. I'll probably give you from Sunday, either Sunday night, Tuesday morning, or Thursday morning, until Sunday midnight to complete both attempts at the exam. What's that? Yeah, I'll have it posted by Thursday morning for sure, but maybe Wednesday night. But I'll probably post it after the session on Wednesday. We have a session on Wednesday. So that's you'll work with it on Blackboard, and I'll give you some more information about what's going to be on it and so on and so forth. It's going to cover everything up to what we did now. It will not cover what we do on Wednesday, which is going to be something called hypothesis testing and the t-test. So I'm not going to have the t-test on it. You'll have the t-distribution over here where you get confidence interval. You got to use t-distribution, but it won't have this material from Wednesday on it.
So if you come on Wednesday here, is it the normal?
You could do it. You could do it here if you want. Yes.
On Wednesday, no, is going to be exam on Wednesday or a normal lecture?
Oh, that's a good question.
Yeah.
I probably won't do an additional lecture on Wednesday.
Okay.
So you can come in here and take the exam here if you want, your first attempt, right? And then you can save your second attempt for some other time.
But then you're saying your review session will be around closer to like
Yeah, exactly.
Thursday, Friday.
Yeah, exactly.
Okay.
Okay, you're right. And then next week we'll get into hypothesis testing and so on and so forth. I think that's the way the syllabus is set up, that I reserved like 2 nights for the exam itself. Yeah. Okay. So I think that's, and I think the dates are a little bit different because I've been modifying this to like, try and, I've been tracking, like I track how many people are working on the assignments and have completed the assignments, how well they're doing on it. So you'll notice that I may not stick completely to the syllabus because I'm trying to figure out, if you guys are keeping up or not. So that's why I might be a little bit slower, a little bit faster in some segments because I'm kind of making a judgment. What's that?
We're kind of going a little bit faster for the June 24th.
Yeah. It was after that. Yeah. Actually, the syllabus, that syllabus is terrible. So at any rate, at some point I'll get around to modifying syllabus so it matches what we're doing. Okay. So, and the other thing is I want to get this in for this exam because this exam is a non-cumulative. So if we get this out of the way, you don't have to deal with this on the second exam. Okay, so you have a little less because the second exam's got a lot of different kinds of tests on it. So there's going to be a little bit more challenging material in second exam. So I want to get more of it done in the first exam, so you guys don't have to deal with it on prepping for the second exam. Okay, do you feel better than when you came in here?
Yeah.
Okay, good. I'm glad to hear that. That's all I want to hear. As long as you feel better than when you came in here, things are good. Okay, so guys online, if you're still there, good night, and I'll have the exam posted for you by Wednesday night. Or actually, I'm gonna have to do it before class on Wednesday. I'll have to have the exam. So if you want, you can come in here, take the exam here. Okay, in which case, I'll be here if there's any questions or issues on the exam. You'll hear from it directly from me as you're taking it. However, if you're taking it time shifted some other time and you come across an issue on the exam, you're kind of stuck on the first try, right? But you can post a question on the discussions forum and say, gee, this is confusing, this question here, I don't understand, or I think this is worded incorrectly, or I think there's a mistake here or something like that. You're gonna be stuck posting that on the discussions forum. And I will look at it. I'll check them pretty much daily to see if there's any questions on the exam, and I'll respond to them and if there's any clarifications that are necessary. So if you have any issues, post them on Blackboard on the discussions forum, and you should have them resolved before you take the second try on the exam. That's one of the reasons why I give you a second attempt, because when we're doing this online, it's so hard to like communicate, like there's always a lag going back and forth on that kind of stuff. Okay, so for you guys online, good night. Okay, I'm chasing these people out because they don't look like they're ever going to want to go home. So good night to you guys online.